For AP Physics air resistance problems. I'm going to do a couple old AP free response problems. This first one says an object of mass m moving along the x-axis with velocity v is slowed by this force, negative kV. So there's my resistive force that's going against the velocity, where k is constant. At time 0, the object has a velocity v naught when it's at position 0 at time 0, as shown above. What's the initial acceleration, magnitude and direction, produced by the resistance force? And so, what I'm going to do is, I'm going to say, well, I'm trying to find acceleration. You say, the way I'm going to get acceleration is from sigma F equals ma, of course. I'm not going to be using kinematics on this. We don't have a constant force. We're not going to have a constant acceleration. We are going to have to go ahead and use F equals ma. Of course, we're doing this for the x-axis. Hey, this thing was already moving on to the right. The only horizontal force acting is this minus kV. So I'm just going to have minus kV. Okay, and that negative is there to show that the force is in the opposite direction of the velocity, is ma. Now, specifically, they want the initial acceleration. So k is a constant. It's not changing. The v is going to be changing, though. If I want the initial acceleration, I'm going to need to use the initial velocity. And the mass is a constant. Okay. Last thing, we want the acceleration, so I need to get the acceleration by itself. So I'm just going to divide through by m. I'll have negative k over m times v naught is a naught. All right, and there's my answer for part A. All right. Okay, moving on. Part B says derive an equation for velocity as a function of time and sketch the function on the axes. Let a velocity directed to the right be the positive direction. Okay, so we want an equation of velocity as a function of time. So what we're going to do to find velocity as a function of time. All right. Find v of t. We're going to start with, once again, sigma F equals ma. When I put in my equation for that resistive force, kV naught, whoa, we don't want v naught. Now it's just negative kV. Sorry, it wasn't the initial. We want the general case. We want to find velocity at any time. So our generic velocity, sorry about that, is going to be my mass times acceleration. Now my point is, my goal here is to find v as a function of t. So the way I'm going to get time involved is where it says a, we're going to substitute in dv dt. All right, because my acceleration is the rate of change of velocity. That's a base definition of acceleration. Okay, so I have an expression now, all right, and I recognize that in that expression, I have a variable and its derivative. This is what we call a differential equation. And differential equations have their own special rules and techniques to solve. This one, we're going to solve by a technique called separation of variables. And what that means is that we're going to try to get all of our terms dealing with time on one side and all of our terms dealing with velocity on the other side. Right? What follows here is going to be just a little bit of rearranging, a little bit of calculus, right? If you are watching this in first semester, you may not have covered this in your calculus course yet, so don't sweat it. But it is something that you will see in your first year calc course. By the time the AP exam rolls around the spring, you'll have covered this. It turns out that there are some things we're going to take a look at in next semester in circuits that the math behind them is just like this. We'll be looking at charge flowing on and off a device called a capacitor and looking at that flow of charge per second. Guess what that's going to be? You say, I can find the charge that's on the capacitor as a function of time. The math will be the same. At that point, you'll have seen enough in your math class to follow along. And we'll go through that, and we'll refer back to this, and everything will be fine. So I'm going to show a few steps here. Don't sweat the details yet. All right. So here's what I'm going to do. I want to separate my variables. I want to get all my V's and dV's on one side and all my T's and dT's on the other. The way I like to do this is the first step I'm going to do is get a coefficient of +1 on my variable. Okay, that's just the first step I like to do. So I'm going to divide through by -k. If I do that, I will get v is -m over k dv dt. Okay, all right. And now the next step then is I'm just going to go ahead and get the dv by itself. So it sounds like I'm pushing it to one side and pushing it back. That's because I am. Multiply through by -k over m. And it's like I'm multiplying by dt, almost like dv and dt are two different variables, and I'm doing a division here. That's not what's going on. It just looks that way. I'm not going to get into the subtle details. Thank goodness I don't have to explain that because, you know, it's a math thing. But essentially, and I'm going to divide through both sides by v. And so I'll end up with this. All right. So, yeah, I know what that looks like. It's not exactly what happened. Okay, at this point, I've got all my t's and dt's on one side and my v's and dv's on the other. So what I'm going to do is I am now going to integrate. Okay, so I'm going to look at what's happening over time, adding it up a little bit of time at a time at each little interval. Boom, 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 adding up all my dt's. And while I do that, I'll be adding up what happens to my velocities and change velocities over time. But I'm going to have a bunch of infinite number of little dt's that I'm going to add all up, and the results of an infinite number of little dv's I'm adding all up here. I'm going to do this from the starting time to any future time. So this upper bound on my integral is going to be a variable t. Okay. Well, meanwhile, I want to look at what happens to the velocity. From the velocity, my bounds have to be in terms of the variable. So these bounds are going to be in terms of v, but my bounds have to correspond to each other. So time 0, that's when the v was v naught. To any future t, so this will be any future v. So I'm going to get v as a function of time. Okay, now integrating this, this is actually a pretty straightforward integral because these are all constants. So the integral of that is just going to be -k over m times t, evaluated from 0 to t. And on the other side, I'm going to have integral of 1 over v dv. That's going to be natural log of absolute value of v, evaluated from v naught to v. All right. When I evaluate this, I'm going to put the final bound in minus what I get when I put the initial bound in for t. Okay, putting t in for t, that's just this -k over mt. Putting a 0 for t, that would just be 0 then. So it's just that. On the other side, what I get when I do the final minus initial, so put the final v in for v, that'll just be natural log absolute value of v, minus when I put the lower bound in, put v naught in there, that'll be natural log absolute value of v naught. All right, taking a look at this. I have two logarithms that I'm subtracting. They're the same base. They're both base e. When you do that, a property of logarithms, when you have a subtraction with the same base, you can just turn that into a division. So this will be the natural log of v over v naught. All right, -k over mt. Now I'm going to undo the logarithm. I'm going to exponentiate this. I know that logarithm means this is a log base e. So this is e to this power equals v over v naught. That's the way logarithms work. So e to the -k over mt is v over v naught. I'm going to go ahead and move the v naught over. And look what I have. I have v naught is, sorry, I got v is v naught times e to the minus k over mt. All right. Okay, this is my exponent here on the e. All right. Now what's interesting here, okay, is of course that this chunk, this e to the minus k over mt, if I go from t is 0 to as t approaches infinity, when time is 0, e to the 0 power is 1. And when time is infinite, e to the negative infinity, that would be 0. So as time goes here, from 0 to infinity, the value of that goes from 1 to 0. You say, well, this is going to be a decimal between 1 and 0. This is like the percentage of v naught. That's my starting value, which is the fastest this thing's going to be going. is V naught. It's going to get slower and slower because of that resistive force pushing against the motion. It's going to slow down. So this is showing me the percentage of V naught that I'm at. Okay, is what this equation for V is going to tell me. So that's it. So that's kind of neat the way that works out. Point is, this is an exponential decay curve. So if I go to draw my graph, all right, then, oh, what the heck, we'll do it right on the original sketch for the graph. All right. I know it's going to be an exponential decay curve, but I don't need to do this calculation to graph it, okay? I can just logically say, thinking about this, that this thing is going to start with V naught. So my graph has to start at V naught. I'm going to start there. And I'm moving to the right, velocity is right, but the force, and therefore the acceleration is to the left. It's the negative acceleration, positive velocity. I'm going to get slower. My velocity is going to head towards 0. But I recognize that as I go along, the force pushing against me, as I get slower, because the force depends on V, as I get slower, the force gets less, so the acceleration gets less. The acceleration on a velocity graph is the slope. So I'm going real fast. I got a big force against me at the start, a big negative slope, really steep. But as I go on, that force gets smaller and smaller as the velocity gets smaller. So the slope gets less and less and less. This graph is going to start to flatten out. At the very end, as my V approaches 0, which, yes, we know to get to 0 would take an infinite amount of time. You say as it approaches 0, then the slope would approach 0. It's going to be leveling off, and it's going to take infinite time for this thing to get to 0. So it's going to be asymptotic to 0. I got this asymptote here. Okay, and that's my VT graph. They'd like me now to derive an equation for the distance it travels as a function of time t and sketch this function on the axes below. Okay, to get the function, we're going to have to use the equation we just got. This is an equation for velocity as a function of time. You know that velocity is the rate of change of position, right? We're trying to get a position equation. This is the derivative of the position equation then, right? The velocity equation. So I'm going to work backwards to get it. So instead of taking a derivative, I'm going to take an integral. So we're going to integrate this. Okay, I'm going to work backwards. Again, we didn't, in this previous part, we did not need to do this calculation, right, in order to get the graph. Like I said, this calculation is something that will be expected of you in the spring, but in the fall semester, you don't need to know this yet. Likewise, for this one, we're going to work backwards and integrate this, something that you may not have seen in your math class yet if it's the fall, but by spring, you'll have seen it, and so you'll want to be able to do this. And you'll refer back to this video then in the spring, and you'll be like, oh, yeah, follow along, it'll be fine. So here we go. Part C. Right. Okay, so we want to find the position as a function of time. Now we have this velocity equation that V is V naught e to the negative k over mt, right? And so what we're going to do is we're going to take the derivative, or integral. We're going to integrate. So my position, I know, is the integral of V with respect to time, right? That's like our working backwards definition, right? Velocity is the derivative of position with respect to time. Velocity, so position is the integral of velocity with respect to time. So I am going to integrate my velocity function, V naught e to the minus k over mt. Now, it turns out like these e to the power things are really easy to take derivatives and integrals of. If I take the derivative, if I was to take the derivative of this, it would be e to the minus k over mt with this coefficient here, negative k over m, kicked out in front as a coefficient. Okay, is what would happen. And that's a whole chain rule thing, right? Multiplied by the derivative of this. Anyway, this function that's inside the other function. Anyway, so the point I'm going to get an A. So if this, right, this is my velocity expression, if this, dt, integrating with respect to time, from time 0 to any future time t, well, actually, I'm trying to find, yes, that's what I'm trying to find, at any time t. Okay, so what I'm going to do is I'm going to say, well, I'm going to work backwards. I'm doing a derivative in reverse when I take an integral. if I had taken the derivative of a function that would give me this, wouldn't it have kicked out a negative k over m in front? But there's no negative k over m, so there must have originally in the position equation been a negative m over k that would have canceled out that negative k over m when I took the derivative. So I'm still going to have this v naught negative m over k e to the minus k over mt, evaluated from 0 to t. When I put in final minus initials, put in the t for t, that's just going to be, again, this, I'm going to put that v naught in there. E to the negative k over mt, and then minus what I get when I put the 0 in. If I put the 0 in, e to the 0 power will just be 1, so it'll just be a minus mv naught over k. Okay, minus minus makes it a plus, so I'm going to have, and you see I've got an mv naught over k, when the minus minus makes it a plus, mv naught over k, and an mv naught over k, so I'm just going to factor that out. And this is like a plus 1 then, you know, when I factor it out. So I put the 1 there, and then minus e to the negative k over mt. Okay, this is what I ended up with as my position equation. Now let's check this chunk out. See this? Look at this from time 0 to time, as time approaches infinity, I should say. Let's make an arrow. It approaches infinite. When time is 0, e to the 0 is 1. 1 minus 1, this thing, this expression here that I bracketed would be 0. As time heads to infinity, right, you say e to the minus infinite, that would be 0. So this would just be 1. So this guy is like, it's a decimal that goes from 0 to 1 for my position. Hey, at time 0, I was at 0 position, so that tracks. When time heads to infinite, put that in there. This comes out to be 1. Guess what my final position is? mv naught over k. That's where I'm going to come to rest eventually as time heads to infinity. That's as far as I'm going to get before I get stopped by this resistive force. Okay, which of course is the answer to part D. Ha ha! Look at that. Typo, looks like a yen symbol. Anyway, point is, so that's it. Hey, can I do the graph for this? You say, of course we can do the graph for this. Position as a function of time. And we say, hey, we're starting at position 0. And we're going in the positive direction. We're going to the right, yeah? We're going in the positive direction. So my graph has to head upward. But I realize that I'm going to be getting slower and slower. And so velocity is the slope of a position time graph. So as I get slower, my velocity gets smaller. My slope gets smaller, 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 smaller. Eventually, if the slope got to 0, that would mean my velocity was 0 and I'd be stopped. It's never quite. It's going to have to head to infinity. For time to be infinite for that velocity to actually go to 0. But it'll be moving so slow that you can't tell the difference. So it's going to do one of these. Right? And it's asymptotically approaching a final value. Hey, what is that final value? That's the value when time approaches infinite. We just figured out, oh, and if this whole bit in brackets is just 1, so it's just mv naught over k is this value right there. That's our final position. And so that is the answer to part D, is that the distance it travels, it starts at position 0, ends at mv naught over k, so the distance traveled is mv naught over k. Ta-da! And that, my friends, is that AP for response problem.